Very good morning, dear students. Welcome back to the online class. So far we have discussed two examples with respect to the power series solutions about an ordinary point. In this class we are going to discuss some more examples, and in the previous class I have given this as homework. I think all of you have tried for this one. Anyhow, I am going to discuss the same example again and few more examples, isn't it? Find the power series solution of y double dash minus xy dash plus x square y is equal to 0 about an ordinary point x equal to 0. So here the given differential equation is the differential equation of second order with variable coefficient we are getting there. For this, before this power series method we are not having any general method, so that's why the method is get existed. With the help of the solutions whatever we are getting for the differential equation with constant coefficients, the nature of that solution they have observed very cleanly and deeply, and then they have found out the method that is called as power series method, so that to get the solutions of the differential equations with variable coefficients, isn't it? And already we have discussed the theory part about the power series method, and we have solved two examples also. And now we are going to discuss the one more example. Here this is the example with variable coefficient we are writing there, and we are going to find the solution of this differential equation about this point, about the point x is equal to x naught, and x naught in the place of x naught we are writing that as 0. It means we are going to verify to get the power series solution of the given differential equation about the point x is equal to x naught, that is equal to 0. We need to show that the point is an ordinary point first if you want to get the solution with the help of power series method, isn't it? So first write down the given differential equation y double dash minus xy dash plus x square y is equal to 0, and coefficient of y double dash must be equal to 1. We need to get there, so already it is 1, so it is already in the standard form. Now write down the coefficient of y dash as p of x. Y dash coefficient of y dash is minus x, and that is equal to p of x, and coefficient of y is x square, and that is q of x we are writing there, isn't it? So now the given point is x is equal to x naught. X naught is 0 they have given there. So now at x equal to x naught they have given particularly as 0. At x equal to x naught, what is the value of p of x and q of x? Substitute x equal to 0 here. 0, you are getting p of 0 is 0, and q of 0 is also 0 itself you are writing there. It means both p of x and q of x becomes finite you are writing there. Therefore at x equal to x naught is equal to 0, both p of x and q of x are finite. As the value of p of x and q of x becomes 0, those values are finite itself. Therefore p of x and q of x are analytic we are writing there. So this implies x equal to x naught is equal to 0 is an ordinary point of the given differential equation. So whenever these two are analytic, at the time we are going to say that the given point is ordinary point for the given differential equation, not for p of x and q of x, isn't it? So it is an ordinary point for the given differential equation we are going to say. As x equal to x naught is an ordinary point of equation number 1, then we are going to assume that the solution of equation number 1 is of the form. It is according to the theory part about the power series method. If the point becomes an ordinary point, at that time we have to assume that the solution for this differential equation in the following form. So that is given in the theory part also, that is given by y is equal to summation. Yes, in the previous case we have considered that as cn x minus x naught to the power n, then also correct, we are getting that as correct. If you are going to take the variable coefficients, then also we are getting the same thing. So am x minus x naught to the power m. So whatever the variable we are going to consider here, the same power we need to consider here, and whatever the variable we have considered here, the summation is running for the same number we have to choose. So that's why I have chosen the different notation for that, the different constant coefficients in that, isn't it? So if you are going to choose here am cn at the time n, if you are going to consider at the time x minus x naught to the power n, and n is running from 0 to infinity, we have to consider this summation is running for n we are getting there at that time. And here we have chosen am and x minus x naught to the power m, that's why summation is also running for m from 0 to infinity. So y is always in the form of summation am x minus x naught to the power m is running from 0 to infinity. And now substitute the value of x naught. So that is equal to summation m is running from 0 to infinity of am x minus x naught value is 0. X naught value is 0 means x to the power m itself we are writing there. So that will we have written. Make this as equation number 2 because x naught value is 0. Then as it is the solution of equation number 1 we have assumed, then we are going to substitute this value in this example. So corresponding to this differential equation, we are going to find the values of am values, isn't it? So that's why we are going to substitute. This is going to satisfy the equation number 1. Then equation number 1 becomes, so substitute the values of y, y dash and y double dash. Y value already we have assumed, and substitute the y dash and y double dash and simplify so that to get the values of the constants. So equation number 1 becomes, so what is the value of y double dash? Y double dash in the case of power series method, summation is always running from 2 to infinity. So 2 times differentiating that this equation, 2 eliminate, some terms will be get eliminated starting from 0 and 1. Those 2 terms will be get eliminated. That's why summation is running from 2 to infinity we are writing there. So summation is running from 2 to infinity. So 2 times differentiation of this term will be m minus 1 am x to the power m minus 2. So m minus 1 am x to the power m minus 2 minus, here in the given differential equation minus sign is there. So minus x into y dash, y dash value is summation m is running from 1 to infinity. Summation m is running from 1 to infinity, because first time differentiation will eliminate only one summation term from the summations of equation number 2, isn't it? So that's why one time differentiation will give the summation is running from 1 to infinity, and the first derivative of this term will be m into am x to the power m minus 1 written there, plus x square will be as it is, and value of y we have substituted here, and that is equal to 0 we are going to equate, isn't it? And after substitution of the value of y, y dash and y double dash, first our aim is what? We are going to multiply the variable coefficients inside the summation first, and then first you have to multiply this. So what we are writing there, here there is no variable coefficient, so we are going to keep this thing as it is. Minus will be as it is. Take x inside the summation. Summation is running from for m from 1 to infinity itself. am x to the power m minus 1 and x to the power 1 we are writing there. X to the power m minus 1 plus 1. So minus 1 plus 1 will get cancels, only x to the power m we are writing there. So plus, take this inside the summation, x to the power m into x to the power 2 we are writing there. So x to the power m plus 2 we are writing there, and summation is running from 0 to infinity. This am will be as it is, and that is equal to 0. So after multiplying each term inside the summation, what our aim is, we are going to convert every summation should be multiple of general power of x. So that is called as x to the power m form we need to get there. So here x to the power m minus 2 written there, here x to the power m. So we are going to keep this thing as it is. Here we need to convert this term in the form of x to the power m, and here also we are going to convert this is in the form of x to the power m. For that what we need to do, so accordingly we need to change the summations are running from where to where. So what we need to do here, substitute m is equal to, to get here x to the power m in the place of m, substitute m, because m only is the thing variable here, isn't it? It is going to vary in the summation. So that's why we are going to substitute for m is equal to m plus 2. If we are going to substitute at the time, 2 and 2 will get cancelled. It is in the form of x to the power m we are writing there. So what we did here, for this m we have added 2 terms. So that's why 2 sum terms we have added for this summation. So that's why a summation was running from 2 to infinity at the time. To add 2 more sum terms, so it takes the m value from 0 to infinity. So 0, 1 and 2 to infinity from the previous term itself. So 0 for summation is running for 0 and 1 we have added, so that 2 sum terms we have added in that summation, so that it is running from 0 to infinity, so that to convert it is multiple of x to the power m we are writing that, isn't it? So if you are going to substitute m is equal to m plus 2, at the time what we are writing here, relation. So substitute m is equal to m plus 2, at the time m is running from 0 to infinity we are writing there. Substitute m is equal to m plus 2, and here m plus 2 minus 1 will be m plus 1, and am plus 2 we are writing there, and x to the power m plus 2 minus 2 will get cancels, so only m we are writing there, x to the power m. So minus summation m is running from 1 to infinity, and here already it is multiple of x to the power m itself, so we are going to keep this thing as it is, plus summation m is running here x to the power m plus 2 written there. m plus 2. To convert this one, we have to subtract. So 2 terms you have to less from the summation. So m is running from sum x to the power m, we have to replace by m minus 2. M minus 2 and plus 2 will get cancelled. So only x to the power m already there. 2 terms you have to less. So summation is running from 0 to infinity. If you are going to less 2 some terms from this one, so summation is running from 2 to infinity. Here we have added, so that's why running from 0 to infinity. If you are going to less 2 some terms from this summation, which is running from 0 to infinity, if you are going to get, that is running from 2 to infinity, isn't it? So summation is running from 2 to infinity. So a substitute m is equal to m minus 2, am minus 2, x to the power m minus 2 plus 2, 2 and minus 2 will get cancelled, so only we are writing x to the power m, and that is equal to 0. So if you are going to expand both the summations, again we are writing the same values. If you are going to expand these both summations, again the value will be same. So let me show that. So from this summation, for m is equal to 2, what we are writing there? Summation is running from 2 to infinity. So for m is equal to 2, this first term, so 2 into bracket 2 minus 1, that is 1 we are writing there, and am, for am means m is equal to 2, a2 x to the power 2 minus 2 will be 0, so there is 1 we are writing there, isn't it? Plus, so for m is equal to 3, what we are writing there? Second term. So for m is equal to 3, 3 into 2, that is 6 we are writing there. So better write down 3 into 2 itself, and am value is, for m is equal to 3 is a3, and x to the power 3 minus 2, that is 1 we are writing there. Plus, for next number, what we are writing there? For m is equal to 4 into 3 we are writing there, because m into m minus 1, and am is a4 we are writing there, x to the power 4 minus 2 will be 2, plus and so on, like that we are getting. So you have converted this summation is running from 0 to infinity by substitution of m is equal to m plus 2. At the time you got this as a relation, and summation is running from 0 to infinity, we are writing there, isn't it? And if you are going to expand this summation, again we have to get the same result. So for m is equal to 0, what we are writing here? For m is equal to 0, 0 plus 2, that is only 2 we are writing there, that is 2 is here, and m plus 1, 0 plus 1 will be 1, that is we are having here. So m is equal to 0, 0 plus 2, that is a2 we are writing there, that is we are having here, x to the power 0, that is 1, so that only we are writing here. So the first term will be there. Next, for m is equal to 1, what we are writing here? For m is equal to 1 plus 2, that is 3 we are having. So m is equal to m is equal to 1, that is 2 we are writing here, that term we are having. For m is equal to 1, a3 we are writing there, that term also we are having. For m is equal to 1, x to the power 1, that is x we are writing there. So the whole term as similar to that of the previous case we are writing there, isn't it? So similarly, for m is equal to 2, 4 into 3 we are writing there, 4 into 3 we are writing there. For m is equal to 2, here a4 we are writing there, that term we are having. For m is equal to 2, x to the power square. So both the summations are same, only summations are running from some number we are get changed, but every summations are having multiple of general power of x we are writing there, isn't it? So general power is x to the power m we have considered, isn't it, as we have assumed in the given example, isn't it? So now every summations are multiple of x to the power m. In this case we are writing there. After this, what we need to observe, summations are running from here to here. This summation is running from 0 to infinity, this summation is running from 1 to infinity, this summation is running from 2 to infinity. So among these summations, which is having the least number of sum terms, summation is running from 0 to, suppose that this is 100, suppose that you are going to consider this as 100, this is also 100, this is also 100. So 0 to 100, and here 1 to 100, here 2 to 100. So which summation is containing the least number of sum terms? Summation is running from 2 to infinity, because start with 2 and ends with 100. Here start with 1 and ends with 100. Start with 0 and ends with 100. So this is containing maximum number of sum terms. This is containing one less sum term than this, and this is containing two sum term less than this summation, and one sum term less than this summation we are writing there, isn't it? So the least sum number will be, summation is running from 2 to infinity we are writing there. So that's why remaining summations are also running from 2 to infinity. We can convert, isn't it? But this we can't convert in the form summation is running from 0 to infinity, isn't it? We can convert, but we are not getting the general power of x to the power m. So we are going to keep x to the power m as it is, and general power of x will be same, we need to get there, such that summations are running from same number we need to do. So that's why these summations we are going to convert in the form of summations are running from 2 to infinity possible. isn't it? By substitution of m is equal to 0, substitution of m is equal to 1. Remaining we are going to write down in the form of summation r running from 2 to infinity and multiple of x to the power m itself. And here substitute m is equal to 1, extract out only one sum term from this summation, and remaining terms are in the form of summations. Summation is running from 2 to infinity itself with multiple of general power of x to the power m itself, and this summation will be as it is. So that same thing we did here. So for m is equal to 0, what we got? So that already we have expanded that summation. So 2a2 we have written there, that we have written, and 6a3, 2 into 3, 6a3x we have written. So two sum terms we have taken outside. We are not going to expand this for m is equal to 3. So remaining terms we are going to write down in the form of summation itself, and that summations are running from 2 to infinity right in there. That summation will be as it is, isn't it? So only two sum terms we have taken outside. Remaining we have written in the form of summation, and summation is running from 2 to infinity as it is. Minus, for this summation, to convert the summation is running from 2 to infinity, we have to substitute m is equal to 1. So minus into each sum term will be each of the term will be minus. So take one summation outside the summation. So for m is equal to 1 a1 x, 1 a1 x we are writing there, 1 a1 x, so only minus a1 x we are writing there, minus remaining summations will be as it is from 2 to infinity, m am x to the power m will be as it is, plus the last summation will be as it is already running from 2 to infinity, which is the least summation, least number of sum terms containing we are getting in the summation, last summation, and that is equal to 0. And now clump the terms multiples of various powers of x. Clump the terms multiples of various powers of x. See here, this is constant multiple, x to the power 0th coefficient. Here it is x to the power 1th coefficient. Here it is x to the power 1th coefficient. And remaining all are x to the power mth coefficient, and all m is running from 0 to 2 to infinity we are in there, isn't it? So that's why 2 times of a2 separately we have written, 6 times of a3 minus this a1 times of x is common taken outside, plus only remaining summations, and all the summations are running from 2 to infinity, that's why summation is also common. And from the first summation, see here, x to the power m, x to the power m, x to the power m. So x to the power m is common, that term we have taken outside as a common. So m plus 2, m plus 1, am plus 2, that we have written, minus m am we have written, minus m am, plus am minus 2 we have written, into x to the power m, and that is equal to 0. So make this as equation number 3. See here, x to the power 0th coefficient separately we have written, x to the power 1th coefficient we have separately written, and in this summation for m is equal to 2, x to the power 2, and here if you are going to substitute m is equal to 2, you are writing one sum term, and that is x to the power 2th term separately, x to the power 2th coefficient separately. For m is equal to 3, x to the power 3th coefficient separately. Like that we are going getting up to infinity, isn't it? So you have clumped the terms multiples of various powers of x separately we did. So that equation is called as equation number 3. Called as equation number 3, and which is an identity equation we are writing there. So once you got an identity equation, then try to get the values of the constants by equating constant multiples of various powers of x to 0. So now we are going to equate the coefficients of various powers of x to 0. Now equate coefficients of various powers of x. This is the coefficient of x to the power 0. This is the coefficient of x to the power 1. This is the coefficient of x to the power 2 also, x to the power 3 also, x to the power 4 also. Like that we are going getting. So we are going to equate the coefficient of various powers of x to RHS side terms, isn't it? And RHS side we are having 0. So now we equate the coefficients of various powers of x to 0 to get the values of a2. Because a0 and a1 we are going to keep as it is. We are not going to alter any in any example, isn't it? So remaining terms we are going to convert a2, a3, a4, so on up to an, and so on. We are going to put down in the form of either multiple of a0 or a1 in terms of a0 and a1. So now we equate the coefficient of various powers of x to 0 to get the value of a2, a3, so on up to an in the and so on in terms of a0 and a1. This implies. So coefficient of x to the power 0 we are going to equate in both the sides. So x to the power 0th coefficient in the LHS side is a2 times of a2. In the RHS side is 0. So that is 0. So 2 is never 2 into a2 is 0, and 2 is never to be 0. Then obviously a2 must be equal to 0 ultimately. And from the second term, So x to the power 1th coefficient we are going to equate to RHS at terms. Coefficient of x to the power 1th coefficient is 0 we are writing there, and here 6a3a1 we are writing there. 6a3a1 is equal to 0. So from this always try to get the value of higher subscript coefficients we are going to calculate. So a3 is equal to a1 divided by 6 we are writing there, that we have written, isn't it? And summation is multiple of x to the power m is equal to 0, and summation is equal to 0 means each of the term is equal to 0 we are writing there. That's why the summation, inside the summation, whatever the term we are writing there, which is the coefficient of x to the power m, that term we are going to equate to 0, and that relation is true for every m is running from 2 to infinity. Every m greater or equal to 2. M is equal to 2 or more than 2 we are writing there. So that's why this relation is true for every m greater than or equal to 2 we are going to consider. So write down this relation. So that relation is m plus 2, m plus 1, am plus 2 minus am plus am minus 2 is equal to 0. This is the relation which is true for m is either equal to 0 or more than, equal to 2 or more than 2 we are writing there, isn't it? So observe the constant coefficients. So from that relation the highest subscript is m plus 2 we are writing there, because here m and m minus 2. So highest subscript is m plus 2. So that's why we are going to calculate the value of am plus 2 from this relation. So am plus 2 we are going to keep as it is. So first we are going to keep this thing as it is, remaining we are going to shift to RHS side. So what we are writing here, am minus am minus 2, and here it is multiple term for this. So shifting this term to RHS side, it is going to divide the RHS side term. So at the time m plus 2, m plus 1 we are writing there, and this relation is true for every m which is greater than or equal to 2 we are writing there, isn't it? So this is the way of finding the recurrence relation. So now from this, for m is equal to 2, already see here our aim is that we are going to calculate the value of a2, a3, a4 and so on. So already a2 value we have calculated and a3 value we have calculated, and from this relation we need to calculate the value of a4, a5 and so on. For m is equal to 2, this relation is true for m is equal to 2 or more than 2. Substitute m is equal to 2, at that time we are writing the value of a4. For m is equal to 2, a4 is equal to 2 times of a2, 2 times of a2 we are writing there, minus a0 we are writing there, divided by m is equal to 2. 2 into 2 is 4, here 4 we are writing there, 4 into 3, that is 12. So a0 value is already 0, so 2 times of a2 value is, a0 we are going to keep as it is, and a2 value is 0, so this value becomes 0, it means a minus a0 divided by 12. So a4 is converted in the form of either a0 or a1 we need to get. So here in terms of a0 we are getting, so we are going to stop the simplifying the value of a4. For m is equal to 3, what we are getting there, here a5 we are getting there, a5 is equal to 3a3 we are getting there, minus 3 minus 2, that is a1 we are getting there, divided by for m is equal to 3, here 5 into 4, that is 20 we are getting there, isn't it? So a3 value is a1 divided by 6, so that we have substituted a1 divided by 6 minus this a1 divided by 20 we are going to keep as it is. 3 1s are 3 2s are written there, so a0 divided by 2 minus a1. So simplifying this one, what we are writing there, minus a0 divided by 2 whole divided by 20 means that is minus a1 divided by 40 we are writing there. So similarly find the value of for m is equal to 4, we are getting that a0 divided by 90, like that we are getting there. Now we are going to substitute these values in equation number 2. Equation number 2 is what we have assumed, it is our assumed solution, and with the assumption we have found the particular value for the constant coefficients, that is a0, a1, a2, a3, a4 and so on, isn't it? And that we are going to replace in that solution. It will becomes the particular solution for the, will becomes the solution for the given differential equation, which is having the variable coefficients. Now substituting these values in equation number 2 we get, so equation number 2 is what, y is equal to summation m is running from 0 to infinity am x to the power m we are writing there. So expand this summation first. For m is equal to 0, so a0 x to the power 0, that is a0 only we are writing there. For m is equal to 1, a1 x plus m is equal to 2, a2 x to the power 2. For m is equal to 3, a3 x to the power 3 plus a4 x to the power 4 plus a5 x to the power 5 plus and so on, like that we are going getting, isn't it? So y is equal to a0 we are going to keep as it is, a1x we are going to keep as it is. Now substitute the values of a2, a3, a4, a5 and so on in terms of either a0 or a1, isn't it? So a2 is 0 plus a3 is a1 divided by 6, a1 divided by 6 into x3, and a4 is a4 value we have found a minus a0 divided by 12 minus a0 divided by 12 times of x to the power 4, and a5 value is a0 minus a1 divided by 40 minus a1 divided by 40 times of x to the power 5, and a6 value is minus a0 divided by 90 times of x to the power 6 plus minus, and so on like that we are getting. Now from this relation clump the terms multiples of a0 separately and a1 separately. So y is equal to a0 we have taken as common outside. From this summation remaining will be 1, and here a0 term is here, so minus a0 we have taken outside, so only minus 1 divided by 12 times of x to the power 4, so minus x to the power 4 divided by 12, and next a0 term is here, so minus x to the power 6 divided by 90 minus x to the power 6 divided by 90 plus minus, and so on like that we are getting, isn't it? Plus clump the terms multiples of a1 separately. A1 we have taken as outside, so first term will be x, and here a1 is here we are writing there, so x cubed divided by 6 minus x raised to 5 divided by 40 plus minus plus, like that we are getting. So you are getting solutions of this form. So now we got y is equal to a0 y1 plus a1 y2 we are writing there. So y1 and y2 are the two independent solutions, so linear combinations of those two will give us the solution for the second order differential equation. For the second order differential equation you are getting the auxiliary equation as second order, it means quadratic equation we are getting there. On solving that quadratic equation you are getting two roots. For the two roots we are getting c1 e to the power m1x plus c2 e to the power m2x, like that we are getting there. That is the solution. So that is c0 c1 y1 and c2 y2 we are getting. That is the solution for given differential equation of second order, isn't it? So like that we are getting the solutions of the given differential equation with the help of power series method. And this, let we glance over next example. So this example already have taken in the first class itself, and for this we are getting the standard solution c1 cos x plus c2 sin x as the solution, isn't it? Already I have discussed that one. And now we are going to observe the next example, y double dash minus y is equal to 0. So in the previous case what we got there, y double dash plus y is equal to 0, and here we are going to resolve this example for y double dash minus y is equal to 0. So the same procedure will be there. Wherever plus we are writing there, we are writing minus sign, and accordingly the value of constants will be get changed. So please try to get the solution for this one in the power of x, isn't it? So I hope it is easy. You please go through this, try to get the solution for this example. Take this example as homework, isn't it? I will deal the next example. So next example, find the power series solution of array's differential equation only in the power of x, only in the power of x. So what is meant by array's differential equation, that we have to keep remember, isn't it? So array's differential equation is the standard differential equation and is given by some particular form, and we are going to get the solution for that differential equation only in the power of x. Only in the power of x means the point given by x0 is equal to 0, isn't it? And which is an ordinary point for that differential equation we need to prove, isn't it? So let us consider the array's differential equation is given by, array's differential equation is given by y double dash plus xy is equal to 0 or y double dash minus xy is equal to 0. So both equations are said to be array's differential equation. In exam if they have given like this array's differential equation, at that time you better go for y double dash plus xy is equal to 0, or if particularly they have given y double dash minus xy is equal to 0, at the time you have to solve this example itself, isn't it? So generally they have given, at the time you have to go for y double dash plus xy is equal to 0, and we will solve both the things here. So one I will solve here, and rest of the thing you have to solve in home, isn't it? As similar to the previous case, isn't it? Now here we are going to consider this first equation. Now from equation number 1, so coefficient of y double dash is 1. At the time the given differential equation in the standard form. Now the coefficient of y dash is the value of p of x. So here p of x value is 0, because y dash is never to be 0, then obviously may be 0 or may not be 0, then to be 0 in all the time the p of x value must be equal to 0. So p of x value will be 0. Next, the coefficient of y will be q of x value will be x. So like that you have to write down, isn't it? The standard form of this one is what? Y double dash plus p of x into y dash plus q of x into y. So p of x term is not there, so that's why that we are noted it as 0, and q of x value is x we are going to consider. And now to get the series solution only in the power of x. So our aim is what? Only in the power of x means we need to take x is equal to x naught, and that x naught value is 0, isn't it? Now at x equal to 0, we have to verify that whether this point is an ordinary point or not. So at x equal to 0, check the value for p of x and q of x. So at x equal to 0, the value of p of x will be 0 and q of x is again 0. Both values are analytic, as we are getting those values are finite, isn't it? So at x equal to x naught, both p of x and q of x are analytic, and this implies x equal to x naught is an ordinary point of equation number 1. Whenever both p of x and q of x are analytic, at the time we are going to say that the given point x is equal to x naught is an ordinary point for the given differential equation, not for p of x and q of x, isn't it? So it is ordinary point of the given differential equation. Now as it becomes an ordinary point for the given differential equation, then we can assume the solution of equation number 1 is of the form this y is equal to summation n is running from 0 to infinity cn x minus x naught to the power n. So again we can take any variable, isn't it? So cn, or you can take am, or we can take cm, isn't it? Cm x minus x naught to the power m is running from 0 to infinity also we can take, then also no problem. Simply more generally we have considered this as cn x minus x naught to the power n is running from 0 to infinity. So substitute the value of x naught, summation is running for n from 0 to infinity, cn x minus x naught is 0, so x to the power n only we are there. Make this as next equation 3. So now equation number 1 becomes, as it is the solution of the given differential equation, then this must be satisfying this equation number 1, then equation number 1 becomes, so y double dash value. So for our power series solution, whenever the point becomes ordinary point, at the time we are going to assume the solution of this form. If we are going to differentiate this equation twice, at the time summation is running from 2 to infinity written there, so summation is running from 2 to infinity. Second differentiation of this inside term, so this is constant, so keep that constant as it is. 2 times differentiation of this one will be n into n minus 1 x to the power n minus 2 plus x y dash we are writing in the given differential equation. X we are going to keep as it is, summation n is running from 0 to infinity. Y value is what? That we have to substitute. Summation is running from 0 to infinity and cn x to the power n, and that is equal to 0. So now this, after substituting the value of y dash and y double dash, you have to multiply each of the term inside the summation first. So this summation we are going to keep as it is, there is no multiple term, plus x inside the summation if you are going to take, at the time cn x to the power n plus 1 we are in there and equating that to 0. And now both the summations are not in the general power of x, isn't it? So to make the general power of x, what we need to convert? We need to convert this both the summations are multiple of x to the power n. So for this we have to add 2 terms. For this what we need to do, one term you have to less. So if you are going to add 2 sum terms, substitute n is equal to n plus 2, isn't it? So directly we can write down, substitute n is equal to n plus 2 and this summation is running from 0 to infinity we are writing there. 2 terms you have to add. So it is 2 to infinity we are writing there. If you are going to add 2 terms, so it becomes 0 to infinity. So 0 to infinity, substitute n is equal to n plus 2, n plus 2, n plus 2 minus 1, that is n plus 1, and cn plus 2, x to the power n plus 2 minus 2, minus 2 n plus 2 will get cancelled, so only x to the power n we are writing there, plus summation. Here substitute n is equal to n minus 1, one term you have to less, so 0 to infinity is there. If you are going to remove one term, so it is running from 1 to infinity are there. Summation is running from 1 to infinity. Substitute n is equal to n minus 1, cn minus 1, x to the power n, and that is equal to 0. Now both the summations are multiple of x to the power n, and then we are going to observe the summations are running from where to where. Summation is running from 0 to infinity, and here it is running from 1 to infinity. Which is the summation containing least number of sum terms? Summation is running from 1 to infinity is the containing least number of sum terms than that of this summation. This summation is containing one sum term more than this where it is, isn't it? For 0, isn't it? So that's why this summation is also convert from 1 to infinity by substitution of n is equal to 0 in that. So substitute n is equal to 0. So 2 into 1, that is 2, c2 x to the power 0 in there. One term we have removed out, remaining are running from 1 to infinity, plus summation is running from 1 to infinity, n plus 2, n plus 1, cn plus 2 x to the power n, and this summation will be as it is and equating to 0. If you are perfect in simplifying, at that time remove one sum term from this summation, and both the summations are running from 1 to infinity. At that time directly write down this term. So summation is running from 1 to infinity, and from this term we are going to take x to the power n as common from both the summations. So we have taken outside, and remaining terms we have written as it is: n plus 2, n plus 1, cn plus 2, and from this summation what we are writing there, cn minus 1, isn't it, into x to the power n, that is equal to 0. Make this as equation number 4. Now this equation becomes an identity equation. Coefficient of x to the power 0 we have written as it is separately. For n is equal to 1, x to the power 1th coefficient. For n is equal to 2, x to the power 2th coefficient. For n is equal to 3, x to the power 3 coefficient. Like that we are going getting. So that's why it is called as an identity equation. We have clumped the terms multiples of various powers of x separately, isn't it? So that's why this becomes an identity equation. So equation number 4 or 3, 4 is an identity equation we are getting there. So how we are getting this? So two equations we are getting, that's why we are getting equation number 4. So now it becomes an identity equation. Now we are going to equate the coefficients of various powers of x to RHS items, isn't it? So 2 times of C2 is equal to RHS x to the power 0th coefficient is 0. So 2 times of C2 is equal to 0. So product of 2 terms is equal to 0, but then any one of these must be equal to 0. 2 is never to be 0, then obviously C2 must be equal to 0. Next, from this relation, summation is equal to 0 means each of the sum term must be equal to 0. So this summation n plus 1, cn plus 2 plus cn minus 1 is equal to 0. It is true for every n greater than or equal to 1, because summation is running from 1 to infinity. Either n is equal to 1 or more than 1 we are in there. So that's why it is true for every n greater than or equal to 1 we have chosen, isn't it? So that we have to keep remember. It is depending on the summation running from where to where, isn't it? And observe the relation. This is the recurrence relation we are writing there. From that relation, which is the highest subscript, here we are writing n plus 2. So that's why we are going to calculate the value of cn plus 2. Cn plus 2 is equal to, shift this term to this side, so minus cn minus 1, and here it is product of this term, so dividing the RHS term. So n plus 1 divided by, minus cn minus 1 divided by n plus 1 into n plus 2. It is true for every n greater than or equal to 1. Now we are going to calculate the value of, here C2 value we got already. C0 and C1 we are going to keep as it is. C2 value already we got. Now we are going to calculate the value of C3, C4 and so on, like that, isn't it? For n is equal to 1 we are getting obviously C3. C3 is equal to minus C0, and for n is equal to 1, 2 into 3, that is 6 we are getting there. So minus C0 divided by 3 factorial we can write down this one, isn't it? For n is equal to 3. C0 up to this we are writing there. Now for n is equal to 2, what we are writing there? For n is equal to 2, here we are writing C4, and here minus C1, and for n is equal to 2, 3 into 4, that is 12 we are writing there, and this can be written in terms of factorial, that as minus 2 C1 divided by 4 factorial, isn't it? Because 4 factorial means 4 into 3 into 2. But here what we are getting here, for n is equal to 2, here it is 3 into 4 we are getting there. 4 into 3 we are getting, but 2 is not there, so we have multiplied and divided by 2, then we are getting minus 2 C1 divided by 4 factorial we are getting that. This time we can write down in the form of factorial, we are getting this minus 2 C1 divided by 4 factorial, so that we get the more general form of the answer, isn't it? So in terms of factorial we can convert, or you can write down simply as it is, then also no problem. But always try to put the result in the more general form. If it becomes if it is tedious to convert in form of factorial, at that time we are going to keep the things as it is. Now for n is equal to 3, what we are in there? For n is equal to 3, C5 we are in there. C5 minus C2 divided by, here for n is equal to 3, 4 we are in there. 4 into 5, that is 20 we are in there. But the value of C2 itself is 0, that's why this whole term becomes 0. Next, for n is equal to 4, that is 6 we are in there. C6, and here C3 minus C3, and here for n is equal to 4, 5 into 6, 30 we are in there, that we have written. So C3 value already we have found that as minus C0 divided by 3 factorial, so minus C0 divided by 180, that is we can convert that in the form of 4 times of, let's see, 30 means what we are getting here. Here for n is equal to 4, 5 into 6 we are getting there. 5 into 6 we are getting there. And C3 value is what? 3 factorial. 3 factorial means what we are getting there? 3 into 2 we are getting there. So 2, 3, 4 is not there, so we have to multiply and divide it by 4. 4 C0 divided by 6 factorial itself. So minus already we are having, and C3 value is again in terms of minus, so minus into minus becomes plus. We are writing there plus, we are writing, so that's why we are writing that answer as in terms of plus 4 C0 divided by 6 factorial. Now our required solution becomes required, it means assumed solution y is equal to summation n is running from 0 to infinity of Cn x to the power n. Expand that summation and substitute the values. C0 will be as it is, C1x will be as it is, plus C2 value is 0, we have substituted, and C3 value is minus C0 divided by 3 factorial into x cube, and C4 value is C4 value is minus 2 C1 divided by 4 factorial minus 2 C1 divided by 4 factorial into x to the power 4, and C5 value is again 0, plus C6 value is 4 C0 divided by 6 factorial, 4 C0 divided by 6 factorial into x to the power 6, plus and so on like that. We are going getting, isn't it? So now clump the terms multiples of C0 separately and C1 separately. Y is equal to C0, and the first term if you are going to take as common, so 1 we are writing there, and here C0 common means x cubed divided by 3 factorial, and next x0 C0 is common means 4x to the power 6 divided by 6 factorial minus plus minus like that we are going getting, plus C1 if you are going to take as common, first term will be x, and here 2x to the power 4 divided by 4 factorial like that we are going getting, plus minus and so on. So this is the required solution we are getting there, isn't it? So similarly from equation number 2, second differential equation, we can get the solution. Please try that in home. I hope all of you will get. Only the change is what, minus sign. The same procedure will be there, and simply we are going to calculate the value of the constant, and we are going to substitute those values in the relation, so that you are getting this as the terms, isn't it? So now in the next class we are going to discuss the rest of the examples that we will see in the next class. Try to get the solution for array's second differential equation, that is equation number 2, as well as y double dash minus y is equal to 0. For this we are going to get the, you please try this in home. If you are having any confusions, please let me know. I will explain personally, isn't it? See you in the next class.